I'm continuing here with the semiconductor in equilibrium because we have already started with the analysis of the extrinsic semiconductors, and in the extrinsic semiconductors we have already derived so we have already derived the position of Fermi level, that is in n-type, and the Fermi level in the p-type semiconductor with respect to the intrinsic Fermi level, that is EFI. Now, here are a few more key concepts regarding the Fermi level. If you remember from the last lecture, we have derived EFN minus EFI equals to KT ln of ND upon Ni, and for a p-type semiconductor it is EFI minus EFP equals to KT ln of Na upon Ni. Alright, yeah, where Ni is the intrinsic carrier concentration. Yeah. Or we also know that Nd is almost equal to N naught and Na is almost equal to P naught. So these expressions can also be rewritten as EFN minus EFI KT ln N naught upon Ni, and EFI minus EFP KT ln P naught upon Ni. So this is the same expression which is given in your book in the section 3.7.1. Yeah. Now, furthermore, we have two very important dependencies of the Fermi level upon the doping as well as on the temperature. If you have already the book, that is the Donald A. Nieman, you can check in the section which is following this derivation regarding the variation of Fermi energy with respect to the doping and temperature. So I'll simply show you here that let us first take because see, K is a constant, temperature is also a constant, and this Nd and Ni is also constant. But when we take a semiconductor is fixed, we can vary the temperature and we can vary the doping, whereas the intrinsic concentration remains a constant. So let us first make one graph like this. Okay. So this thing is the energy. This thing is the energy E. And let us draw a middle line like this, which stands for the intrinsic Fermi level, that is EFI, that is intrinsic Fermi level. And let's say we have EFN yeah. Now Let's say on this very side we are varying the acceptor concentration Na per centimeter cube. Okay, and on the top let's draw one more straight line like this. Okay, yeah, which stands for Nd, that is per centimeter cube. It's -3. Yeah. So starting from a very low value, for example 10 to the power of 12, increasing it to say 10 to the power of 13, 10 to the power of 14, and so on and so forth up to 10 to the power of 18. And same is the scale on the top side. So that is 10 to the power of 12, 10 to the power of 13, 10 to the power of 14, and let me go to the last value, that is 10 to the power of 18. Alright, now let's say this energy is the bottom of the valence band, it's EV, and this energy is the top of the conduction band, EC, and in between we have the intrinsic Fermi level. Now for an extrinsic semiconductor we have to see, let's suppose for an N-type, how the Fermi energy is going to change with respect to the doping concentration and with reference to the intrinsic Fermi level position. Okay, so I may recall that the Fermi level is the level for temperatures greater than 0, or at the room temperature it is a level where the probability of finding the electron is high, and for an N-type semiconductor the Fermi energy is above the intrinsic Fermi level. So when the doping is quite small, the Fermi level will be closer to the intrinsic Fermi level, and so it will be closer to the Fermi level. When the doping increases, the number of electrons which are present in the donor energy will increase, so the Fermi level will move closer to the donor energy level. So as much as we go on increasing the concentration of the dopants, because the dopants in case of an N-type semiconductor are the electrons, so the Fermi energy will move more towards the donor level. So this will look something like this. So that is, as you increase the doping along this side, the Fermi energy, that is, let me say this is the Fermi level, EF, okay, Fermi level, and I'll also write it as Fermi level. Okay, so Fermi level moves like this. So this is for an N-type. Same is the case for a P-type. So for a P-type, the Fermi energy in a P-type extrinsic semiconductor lies below the intrinsic Fermi level, because when we go on adding the acceptor atoms, the number of holes increases. So the Fermi level moves more towards the valence band. That is to that level where there is the presence of electrons. So the opposite, the same will occur on this side. So it is like this. Although it's a straight line. So so it will be like this. Why? Because now we know the reason, because as we increase the donor or the acceptor concentration, wherever the number of electrons is increasing or decreasing, the Fermi level will move more towards that side. So it is, yeah. So this is again the position of the Fermi level. When the doping is the lowest, the Fermi level in an extrinsic semiconductor is closer to the intrinsic Fermi level. And when it is and when it is increasing, obviously the Fermi level will move more towards the closer to the valence band. So this is for a p-type. So this is for a p-type, and again this is the Fermi level. So from here we can conclude that the Fermi energy EF is a function of the doping concentration, whether it is the donor or it is the acceptor, but it is a function of the doping concentration. So this is one important graph. And then the next one, yeah, the next one is again that we draw the same graph, that is we have all right. Okay, so that is we have the intrinsic Fermi level here and the valence band below and the conduction band on the top. Yeah, so now let's say that this is towards the conduction band. This is the top of the valence band. Okay. Yeah. And if we are drawing it for the silicon, we know that the silicon has a band gap of 1.2 electron volts. Right. Okay. So that is the distance between the two, is like this. And now let us suppose that this is the intrinsic Fermi level EFI. Now, here we'll vary the doping for various graphs, but the scale would be the temperature. That is temperature in Kelvin. Okay. So let's increase the temperature from 0 to 100 to 200, 300, 400, 500 and 600. Okay. Now for the N-type semiconductor, let us first suppose that the doping is 10 to the power of 12. So when the doping is 10 to the power of 12 and we are increasing the temperature from 0 to some high value, what will happen is that the Fermi level will move closer to the intrinsic Fermi level. Why? Because the intrinsic concentration is a strong function of the temperature. If you remember that intrinsic concentration increases with the temperature to the power of 3 by 2, that is 1.5. So when for even a fixed donor concentration, that is 10 to the power of 12, when we increase the temperature, the Fermi level moves towards the intrinsic Fermi level. Alright, now suppose we are going to increase the concentration from 10 to the power of 12 to 10 to the power of 14. Now what is going to happen? How will the graph look like? That is, increase the concentration from 10 to the power of 12 to 10 to the power of 14. Our Fermi level will reach the intrinsic Fermi level, but now it will reach at a very high temperature because the concentration of the donor atoms is increased, so the donor electrons will be much more. The Fermi level will need a larger temperature to move to the intrinsic carrier concentration, that is 10 to the power of 14. So similarly, like this. And obviously for the p-type semiconductor, the same will happen. So it's like this. So let it be, this is 10 to the power of 12, 10 to the power of 14, 10 to the power of 16, 10 to the power of 18. So similarly 10 to the power of, this is a concentration, 10 to the power of 18. Or the graphs can be, you can make them more elongated, in the sense that yeah, we can make them like this. Yeah. And similarly along the P side. And similarly along the P side, like this. So I'm drawing it roughly over here. Okay. Yeah, so that is as we increase the temperature, and the donor concentration also increases, 10 to the power of 16, 10 to the power of 18. So donor concentration also increases at a very high temperature. The Fermi level will reach to the intrinsic Fermi level. That means here it becomes an intrinsic semiconductor. At this point, that is it for a donor concentration. Here it becomes a intrinsic, here it becomes an intrinsic, here it becomes an intrinsic. That is the property where it loses the extrinsic characteristics and becomes the intrinsic. Okay, so this was these were some of the key concepts which were left with us in the Fermi level. Now let us move back to the some analysis of the extrinsic semiconductor. So what we'll introduce here is, I'll introduce you to the concept of the complete ionization and freeze out. So before we discuss these two topics in detail, let's just again recall the distribution of the electrons in the donor level, which is given by the function Nd divided by 1 plus 1 upon 2 exponential Ed minus Ef upon Kt. Okay. Now, if the condition is that Ed minus Ef is much greater than Kt, then obviously this expression Nd would be equal to Nd upon 1 by 2 exponent Ed minus Ef upon Kt, which will be twice Nd upon exponent Ed minus Ef upon Kt. Alright. So, yeah. Now, We know that the total number of electrons in this n-type semiconductor would be equal to the number of electrons in the donor state plus the thermal equilibrium electrons, or we can say the intrinsic electrons. Right? Now, what will be the relative number of electrons in donor state to the total number of electrons? It will be Nd upon Nd plus N naught. So you can just put up the expressions for Nd and N naught, and what we'll get is 1 upon 1 plus Nc by 2 Nd exponent minus Ec minus Ed upon Kt. So this gives you the relative number of electrons in the donor states. Okay. Now let us say we have a temperature of 300 Kelvin and we have the silicon as the semiconductor, where we are doping a phosphorus atoms with the doping concentration of 10 to the power of 16 per centimeter cube. Okay, so we have to determine the fraction of total electrons which are still in the donor states. Okay, so how will we proceed? That is to find fraction of electrons in the donor state. That is, we'll simply put up the values in the above expression, because the fraction of electrons in the donor state will be given by this Nd divided by Nd plus N naught. So it is 1 upon 1 plus Nc. Nc is a constant value, that is the density of the states in the conduction band, 2.8 into 10 to the power of 19 upon 2 into Nd, that is 10 to the power of 16, and its exponent of okay, minus 0.045 upon 0.0259. So that comes out to be, after solving, 0.0041, which is 0.41%. So what does this mean? This means that the number of electrons in the donor state is only 0.41% of total electrons, which means that most of electrons in the donor state are ionized, right? Similarly, for a p-type semiconductor, all acceptor states are ionized. Okay. Now, what is the so this is EFI, this is EF, EV, and EC. Similarly, EFI, EC, EV, and EA. Okay, so it's not EF, it is ED, that is the donor level. So as we said that at the room temperature, all the donor states will be ionized and all the acceptor states will be ionized. So we'll see at T equals to 300 Kelvin. What will happen? That is, each of the donor state holding one electron like this would have donated its electron to the conduction band like this. Okay, so now we have electrons in the conduction band, and in turn what have they become? They have become Nd positive. And similarly, the acceptor atoms, they have a vacancy, that is, they are first positive. They have a vacancy of a hole, they have a vacancy of an electron. So they have accepted the electron from the valence band. That is, they have accepted electron from They have accepted electron like this. Okay, because at the room temperature the electrons get agitated, they get enough thermal energy so that they could jump to the nearest energy level where there is the deficiency of the electrons. Okay, and in turn they have become Na negative. So Nd positive all ionized, Nd negative, Na negative all ionized. So this is P type and this one is N type. So this is what is complete ionization. Now, another important thing is, okay, we have figured it out that it is for at the room temperature that complete ionization occurs. But what about when temperature is 0 Kelvin? When temperature is 0 Kelvin, what will happen? The first thing is there will be no thermal energy. Fine. So wherever the electrons are, electrons will stay wherever they are. So if the electrons are in the donor state, they'll stay in the donor state. If they are in the valence band, they'll stay in the valence band. They'll not move up to the acceptor level because they do not have enough energy to jump. Okay. Therefore, the number of electrons in the donor state will be equal to the concentration of atoms in the donor state, because Nd plus, let me use the same notation, capital D. Nd plus will be 0. That means there will be no ionization of the donor atoms. Okay. So now the condition that this Nd becomes equal to Nd, if we see the expression previously, that is Nd. Yeah. So Nd equals to Nd upon this. So this numerator, this term will be equal to the numerator only when the denominator becomes equal to 1. Okay. So let's take it there and we say that this condition occurs when the denominator in Nd equation becomes 0. Sorry, it's 1. If it becomes 0, it would be infinite. If it becomes 1. So that is exponent Ed minus Ef upon Kt should be equal to 0. Now at this condition, since T is equal to 0, so this will occur at exponent of minus infinity, because then only when the exponent of minus infinity, it comes out to be 0. Otherwise exponent of plus infinity would be 1. Now if exponent of minus infinity, this means that the difference of the two is negative. This means Ed is less than Ef. which means that the Fermi energy must be above the donor level, that is ED, at absolute zero. And in the case of a p-type semiconductor, same thing is going to happen, but instead of ED we have EA. So EF, using the same expressions, EF will be greater than E. The Fermi energy would be, no, the Fermi energy will be below acceptor concentration, acceptor level, right? Because there will be no electrons which will be agitated at T equals to 0. So this is the condition which is known as the freeze out. This condition is called freeze out. So complete ionization and freeze out. These are the two opposite things which happen at, we can summarize it as T equals to room temperature, say 300 Kelvin, T equals to 0 Kelvin. Here at T equals to this, you have the complete ionization, and at T equals to 0 Kelvin, you have the carrier freeze out. Now, the opposite things. What are the opposite things which happen here? Okay, complete ionization, that means that is all the impurities ionized. And carrier freeze out, electrons in lowest possible energy states. No ionization. Okay. Now there's an exercise left for you for this topic, which is that you have to derive analytically that at T equals to 0, the Fermi energy EF lies midway between ED and EC for N-type. And similarly, the Fermi energy for a p-type lies midway between EA and EV. So these you have to derive yourself. Okay. That we know that overall a semiconductor is electrically neutral because the sum of the positive and the negative charge is equal to 0. So charge neutrality means there is no net positive or there is no net negative charge. Okay. Now let us first talk about a compensated semiconductor. A compensated Semiconductor. A compensated semiconductor is one which has both the donor and the acceptor impurities present in the same region. So we can have an N-type compensated semiconductor, and we can also have a P-type compensated semiconductor. An N-type compensated semiconductor would be formed if the acceptor impurities are diffused into an N-type material, and P-type compensated semiconductor would be formed if the donor impurities are diffused into a P-type material. And that is in addition to the donor impurities, acceptor atoms Na are also present. Okay, it occurs. An N-type compensated semiconductor occurs when the donor concentration is greater than the acceptor concentration. And for a P-type, we have, in addition to the acceptor impurities, we have the donor impurities, but the acceptor impurities are in majority, that is Na is greater than Nd. Now if Na becomes equal to Nd, that is known as a completely compensated semiconductor, and the characteristics will be more of an intrinsic type. Okay. Now, using a diagram, let us see let's draw a diagram like this. This is EC, conduction band. This is EV. This is the intrinsic Fermi level, EFI. Let's say we have the donor level. Let's say we have the acceptor level. Alright. Now, the donor levels ED, the acceptor level is EA. Now, when temperature increases, that is above 0, what will happen? First, some of the electrons from ED will go into the conduction band. Some of the electrons from EV will go into the acceptor levels. So this becomes ionized, it loses electron. This becomes ionized, it gains electron. Okay. Then there may be some electrons which may directly jump from EV to EC. Those which gain high energy, like this. So these electrons, these are the electrons which are being contributed by the donor states. So these become donor electrons. These become thermal electrons. Okay. And after losing electrons, we have holes here. So these are these holes and these are the other holes. So likewise, these become acceptor holes, because from here the electrons have jumped to the acceptor levels and the holes have been created, and these are the thermal holes. Okay. Now if N D is the total density of the donor atoms, and Na is the total density or the concentration of the acceptor atoms, then the concentration of the ionized donor atoms will be equivalent to total minus the number of electrons. That is, total will include all this minus the number of electrons, because those which are unionized, because these will be these red dashes, these will be unionized because they have not lost the electron. Similarly, these are unionized and their concentration Na negative will be equivalent to total Na minus the holes present in the acceptor level. It's like this. And there may be some condition, like the electrons from donor levels may directly jump to the acceptor level and they may annihilate the holes. Okay, so this is the overall scenario which can occur in a compensated semiconductor, where we have both the donor and the acceptor levels. Now, keeping this band diagram in mind, what will be the charge neutrality? Total positive charge will be equal to the total negative charge total positive will be equal to the total negative. Now, what is the positive charge? One more thing. And these donor electrons and thermal electrons, they become the total electrons, that is N naught. Similarly, the acceptor holes and the thermal holes become the total holes, which is P naught, that is the holes under the thermal equilibrium. Yeah. So, total positive will be equal to the total negative. Total positive will be equal to the ionized donor states plus holes is equal to total negative, which is Na negative plus the electrons. Or we can write N naught plus, what was Na negative equal to? It was equal to Na minus Pa equals to P naught plus Nd minus Nd. That is number of holes in the acceptor level, number of electrons in the donor level. And then N naught plus Na minus Pa equals to P naught plus Nd minus Nd. Now, if we assume complete ionization, then Pa is going to be 0, Nd is going to be 0. It will be N naught plus Na equals to P naught plus Nd. Using the law of mass action, the P naught will be equivalent to Ni square upon N naught. Substituting it there, That's Ni square upon N naught plus Nd. So after, you know, multiplying it, it will be, the equation would become N naught square minus Nd minus Na into N naught minus Ni square would be equal to 0. So this becomes a quadratic equation. So this becomes a quadratic equation, and you're taking Ni square as a constant. The variable is N naught. Variable is N naught, so this becomes a quadratic equation. So you may solve for finding out the roots and take the positive root, because electron concentration cannot be negative. So we'll get N naught equals to Nd minus Na divided by 2 plus square root of Nd minus Na by 2 whole square plus Ni square. Okay, so when Nd is greater than Na, N naught increases, but when Nd is less than Na, N naught decreases. And if Nd is equal to Na, we can see if Nd is equal to Na, our N naught will be equal to Ni. So it will become an intrinsic semiconductor. Okay. And now if we use the expression of, that is, N naught equals to P naught upon Ni square, and substitute in the same equation, we'll get the expression for P naught as P naught, we'll get the expression for P naught as P naught equals to Na minus Nd by 2 plus square root of Na minus Nd by 2 whole square plus Ni square. So again for Na equals to Nd, P naught will be equivalent to Ni. So it becomes intrinsic. Now, when we have a semiconductor which is doped with the n-type impurities, then we say that the total number of electrons is equal to the intrinsic electrons plus the electrons which are contributed by the donor atom. So we can say Nd positive. But this is not actually the case, because what may happen is that the the electrons which are present in the donor states may, like this, like suppose we have an electron here, and suppose we have a thermal hole generated here which has already contributed an electron. So maybe this electron falls to this level to annihilate the hole. So this is annihilate holes. Okay, so the concentration is lesser than this. Now we have come to a very important and the last conclusion of this chapter, which is to see the variation of to analyze the variation of N naught with temperature in Kelvin. So let's start with a very low temperature. Let us say that this is 100, 200, 300, 400, 500, 600 and 700. So all the mechanisms which we have studied till now in this lecture, we'll now try to see it in the graph. So let's say that the concentration is very small and it's 10 to the power of 12, 10 to the power of 13, 10, 14, 10 to the power of 15, 10 to the power of 16 and so on. Now when we start from a very low temperature, what will happen to this total concentration? At a very low temperature, there will be carrier freeze out. Freeze out will occur. Now as we go on increasing the temperature like this, now as the temperature increases, this concentration will start to increase. As we increase the temperature, the concentration will start to increase. Now, when the temperature increases further, there will be a constant graph like this, which is the extrinsic part because it's N naught. Extrinsic characteristics will dominate. Why? Because the donor atoms will lose the electron and go into the conduction band. But when the temperature is increased further, what will happen? Because the donor atoms are limited in number, So when they lose the electron, they'll get completely exhausted. And after that, what will happen when the temperature increases further? There will be an increase in the thermal energy, due to which the electrons from the valence band will go into the conduction band, and there will be the thermal generation of the electrons, or we can say the intrinsic electrons. So it will be like this. So here we'll have the extrinsic characteristics, and here it will be intrinsic characteristics. And at the start, it will be freeze out, carrier freeze out. Here it will be partial ionization. Here it will be complete ionization. Along this part. But here the characteristics would be, here it would be extrinsic, and when the temperature is increased further, it would be intrinsic, because Ni dominates when the temperature becomes greater. That's why I repeatedly tell you that Ni is a function of temperature, and it varies as the temperature raised to the power of 3 by 2. Okay, so I guess, yeah, and for a any compensated semiconductor, if you are given with N naught, or if you are given with P naught, you may find out N naught from the expression which is given, or P naught from the expression which is given, and then the minority carrier concentration may be found using the formula. For example, for example, in an n-type compensated semiconductor, you can find out the minority concentration holds as Ni square upon N naught. So it is Ni square upon, what will be N naught? It will be equal to Nd minus Na. Yeah. And further, you can try out the numericals which are given in your book by yourself. And with this, we complete the chapter 3. Yeah. And the next topic which we are going to start is the semiconductor under non-equilibrium conditions. So if you have any question related to the lecture of today, you can write back.